This program is rated GE. Content carried in here is suitable for general family viewing.
Well, hello viewers, welcome to today's class. My name is Mr. Paul WAWERU. I'm a physics teacher, and today we are looking at a very interesting topic, a Form 4 topic in physics, and this topic is called the electromagnetic spectrum. Now, my viewer, probably you're holding a remote controller right now as you're switching channels. Probably just switched on to this TV station right now. Now, what happens is that as you're using your TV remote controller, you expect something to happen between you pressing a button on the remote controller and the television set. Now, this topic, as we begin, we shall be trying to explain some of these things. Number one, we should be able to describe the complete electromagnetic spectrum. Number two, we shall be able to state the properties of electromagnetic waves. Third, describe the methods of detecting electromagnetic radiations. And fourthly, we shall be in a position to solve some numerical problems involving this equation that we shall be writing, known as C equals F lambda. Now, as we begin, what are some of the definitions that we can make? Number one is electromagnetic spectrum. So we want to make a few definitions. Number one is electromagnetic spectrum. And this is the arrangement of electromagnetic waves according to their frequencies or wavelengths. So when we arrangement of electromagnetic waves according to their frequencies or wavelengths. Now, what do we mean by electromagnetic waves? Now, my viewer, back in Form 2, we said that waves can be categorized generally into two. Number one, we talked about mechanical, and we also talked about electromagnetic, whereby we said mechanical waves do not require, mechanical waves do require a medium for transmission. Whereas we said electromagnetic waves do not require a material medium for transmission. So when we were talking about electromagnetic waves, we said these are transverse waves which result from oscillating electric and magnetic fields at right angles to each other, and they do not require material medium for transmission. And we can give examples. So examples of these electromagnetic waves, they include radio waves, microwaves. We are talking about infrared. We are talking about visible light. We are talking about ultraviolet. And we can also talk about gamma rays or gamma radiation. So this topic is all about describing these electromagnetic waves by way of how they have different frequencies, either increasing or wavelength, increasing or decreasing. So if we, for example, I'm going to arrange them, starting with radio. Going down, we are moving to microwaves. Going down, we are moving to infrared. Going down, we are moving to visible light. Still moving, we are going to ultraviolet. We can talk about X-rays and gamma rays or gamma radiation. So when we arrange these waves and radiations in order of increasing frequency or decreasing wavelength, we end up with what we are calling the electromagnetic spectrum. So as a way of reminder, you can come up with a name. For example, you can say R, M, I, V, U, X, G. You can decide how you can remember this. Now, how do they work? Moving from this side to the right-hand side, that meaning moving from the radio waves all the way to the gamma radiation, what is happening to the frequency? The frequency is actually increasing. And remember, frequency can be defined as the number of complete oscillations per second. So, and moving that way, again, what's happening to the wavelength is actually becoming shorter and shorter. So, we can say that radio waves have got the highest wavelength or the longest wavelength, but the frequency is quite small. On the flip side, gamma, we can say they have got the highest frequency, but the shortest wavelength. So we are realizing two very key points here, that electromagnetic spectrum is always about describing these waves and these radiations in terms of wavelength and in terms of frequency. So so we wanted to show you some slides along the way we shall see whether we can show that. So what are some of the properties of electromagnetic waves? What are some of the properties of electromagnetic waves? So properties of electromagnetic waves. So we can state them very fast. Number one is that they are transverse in nature. So when we say transverse, properties of electromagnetic waves. So we are saying, number one, they are transverse in nature. What that means, the vibration of particles is, if particles are moving up and down, the wave is moving from the left to the right, such that we can describe them in terms of amplitude and in terms of wavelength, as I have shown in this diagram. So these waves, they are transverse in nature, and actually we know that they are as a result of oscillating magnetic and electric fields. Number two, I've just said that they don't require a medium for propagation. What that means, these waves, they can actually travel through space or through vacuum. Number three, they travel at the speed of light. And we all know that the speed of light is actually 3.0 times 10 to the power 8 meters every second. Now, let me just tell you something about this speed. In 1 second, actually, light is capable of going around the Earth almost 7 times. Sometimes you wonder how it's possible to watch a live match that's happening. Let's say you are watching a match is happening in the UK, and it's happening live. This is courtesy of this speed, because what happens, as we shall be seeing much later, the signals coming from the television cameras, they are transmitted via the airwaves at this speed. And since we are seeing that this speed is quite big, that is why it is possible to watch live events, because the information is being transmitted at an extremely high speed. So that's why we're saying this can be close to 7 times around the earth. If you're to shine some light, an EM wave, in that case, it will go around the earth almost 7 times in 1 second. Number 4, these waves, they carry no charge. So that means they are not charged. They are not charged. They are not charged. Hence, not deflected by both electric and magnetic fields. So when looking at another topic by the name cathode rays, we shall see actually those ones are affected. Number 5, they undergo all the properties we talk about when describing waves. They undergo interference, reflection, refraction, among others, including diffraction and polarization. The next thing is that they possess energy in different forms. We shall see what exactly that means. In different forms, and that is given by an equation, a classic equation, that E equals HF. So what that means is that energy of these electromagnetic waves, the energy they possess, will be governed by this equation. And clearly from the equation you can see that E, in this case being the energy, is directly proportional to F. So E is directly proportional to F. So what that means, the higher the frequency, as we talk about frequency, the more the energy the radiation of the wave is going to possess. So H is known as the Planck's constant. Planck's constant, and it's normally 6.63 times 10 to the power minus 34 joule second. So we shall be probably doing one example much later. And the last property for now that you're looking at is that they obey the general wave equation. They obey the general wave equation. They obey the wave equation. And in this case, the equation we are referring to here is that C equals F lambda. In that case, C is what we call the speed of light. And we've just said that that is actually 3.0 times 10 to the power 8. F being the frequency and lambda being the wavelength. Now, I want us to do a quick example here and see how we can apply maybe those two formulas. The first one, we talked about E being equal to HF, and the second one, we are talking about C being equal to F lambda. So let's take this, if you're noting it down. Example number 1. Example number 1, before we look at how these radiations and waves are produced, detected, and later how they are applied. So the question goes, green light, or example, so green light has a wavelength of 5.0 times 10 to the power minus 3 meters. Calculate the energy it emits. Calculate the energy it emits. Now, this kind of a question, very, very common, we have been given. Now, the good thing with physics is that it doesn't matter how big a number looks or whatever, as long as you know how to link up the values. In this case, we have been given two things. What are we given? Number one, we have been given wavelength. And wavelength, we have said, is represented by lambda. It's a Greek letter, lambda. And this is 5.0 times 10 to power minus 3 meters. We also know, since this is going to travel at the speed of light, we know that the speed of light is 3.0 times 10 to power 8 meters every second. We also know the Planck's constant is 6.63 times 10 to power minus 34 joule second. So you then need to ask yourself, among these, what am I going to use in order to get the energy? Going back to our equation, we saw that energy is given by HF. But then, somebody might now want to ask, but we have not been given F. So, somebody now might ask, but we have not been given F. But then, remember, in our other equation, we saw that C equals F lambda. In this case, therefore, we can try to make F the subject of the formula. So let's do that. We are going to apply mathematics, making lambda the subject of the formula. So we shall have to divide both sides by F. So you'll find that lambda is equal to C over F. And in this case, F is C over lambda. So the best thing to use then would be F equals C over lambda. So we take it back to our formula here. We shall realize that E equals H. Now in place of F, we shall just write C over lambda. And then we just now need to substitute. H is 6.63 times 10 to power minus 34 times C 3.0 times 10 to power 8. And remember, again, in physics, we advise students to work with SI units, System International Units. Now, we have the wavelength is actually in SI units, so it is 5.0 times 10 to power minus 3. So in this case, we shall just now need to use our calculators, and this I'll leave it open. By the end of this lesson, my viewer, I expect you shall have calculated this. Apply the laws of indices. You know, when we take this power to the numerator, changes from minus to positive, and then we shall add this. So that is part of the assignment. Question number 2. So I'll want to see by the end of the lesson how many we will have gotten the correct answer. So moving on to question number 2. The question goes, a certain FM radio station, so this is how the question goes. A certain FM radio station broadcasts at 100.3 megahertz. So, like for example, when we are tuning our radio receivers, we talk about 100.3, 106.7, 99.2. So, when we say that a certain radio station is broadcasting at 100.3 megahertz, then you're asked, calculate. You're supposed to calculate the wavelength of the broadcast signal. Calculate the wavelength of the broadcast signal. Now, this kind of a question, again, we just, like this other one, we just now need to know what are we given. In this case, we are given the frequency and we are supposed to find the wavelength. So, you just need now to write given F is equal to 100.3 megahertz. What you don't have is wavelength. So between the two equations, which one applies? Obviously, the second one will apply in this case because we know that C is given by 3.0 times 10 to the power 8 meters per second. And we've applied this equation, we can find what lambda is going to be. Making lambda the subject, we have already done that. So we saw that lambda is simply given by C over F. And we see that C in this case is always 3.0 times 10 to the power 8. And frequency is 100.3 megahertz. Now, somebody would ask, what does this megahertz mean? Like when you say, I'm tuning on 100.3 megahertz on the FM. What that means is that this is transmitting at a frequency of 100.3 million hertz. So if you try this in actual number, so you just have to say it is 100.3 times 10 to the power mega means power 6. And if we write this in SI unit, you see that the decimal point is here, so we shall have to move it 2 steps to the left. So we shall end up with 1.003 times 10 to the power hot. So when you take it to the left, the power will increase by the number of steps. In this case, we have moved the decimal point 2 steps, so that's going to be 8. So you just see it's simply going to be 1.003 times 10 to the power 8. And if you do this, you can see that the answer is going to be very, very close to around 1 meter. An approximation. So if you use your calculator again by the end of this lesson, just see whether that is the answer. And actually, that is the answer. So these two are very important. The first being that energy is given by HF, and number 2, that C is given by F lambda. Very important equations which we shall be applying even in other topics, including the photoelectric effect. Now, we want to delve right in production and detection of electromagnetic waves. Production and detection. So, how are these produced and how are they detected? So, we want to see production and detection of electromagnetic waves. And this now will form the basis of all the modern day technologies that we have been enjoying. Like the very first one, in this case, we are talking about radio waves. Radio waves. So, how are radio waves produced? Actually, radio waves are produced by oscillating electrical circuits and transmitted through areas or antenna. So there is a circuit that constitutes a few other components which makes an oscillation of electrical and magnetic fields. So as they oscillate, radio waves are produced, and for transmission you need to have an antenna or an area. So that's why you find on top of buildings, skyscrapers, or even for telecommunication. So assume this is a building, you normally see some antenna with some discs and other telecommunication gadgets. So these antenna are responsible for transmission. They need to be up high so that they can be above obstacles, so that the signal can go as far as possible, because these waves, you are saying they are traveling very fast. Sometimes they could be interfered with. And how do you detect? So for the detection part, you need special circuits containing diodes. Again, much later, in a topic called electronics, we learned the various types of diodes that are there. Some are called PN junction diodes. We have crystal radio diodes and so on and so forth. So these circuits containing diodes are used to receive or to detect radio waves, and that's probably what you use on your radio as you're tuning. And for the tuning, again, we shall learn much later. We are using capacitors. So for the other type of wave, in this case, microwaves. Microwaves, we all know, because probably we warm our food in a microwave oven. So these waves are produced in special vacuum tubes called magnetrons. So inside a microwave oven, you'd find a magnetron, and that magnetron causes the vibrations and the oscillations of those magnetic and electric fields, thereby generating microwaves. And these microwaves can also be generated using a mesa. So a mesa, it's just like the way you talk about lasers. Mesa is microwave amplification. How are they actually detected? These are detected using solid state diodes. So I've talked about diodes. So we see that diodes are not only used in radio waves, but also used in microwaves. So we have special circuits containing diodes, and they are used to detect microwaves. We also have what you call dry crystal detectors. Moving on to the next one, we're talking about infrared. Infrared now, if you happen to be holding a remote controller and pointing it at the TV and switching between channels, you are actually interacting with infrared. Where can infrared come from? Number one, it can be from things like the sun, special circuits, hot objects or hot bodies. So all these produce infrared. And for the detection, of course, if you're out in the sun, you feel that heating sensation on the skin. You can as well use thermometer, which are blackened with a blackened bulb, as well as some other types of thermometers you call bolometers. So they'll just give you a visual map of what the environment looks like. And some of the animals actually, they have infrared capability of seeing. So they're able to see things that produce heat. That's why some of the animals are able to detect maybe, let's say, a wild animal is able to detect another animal hiding, courtesy of infrared, because any living thing is able to produce or produces infrared. So you can detect using a blackened bulb, a bolometer, a thermopile, and of course the heating sensation on the skin. Moving on next to visible light. This is pretty obvious. It's absolutely what we use in our daily lives for vision. So where does light come from? Of course, it can come from the sun. It can come from any object that glows. So we expect visible light to come from anything that glows, including some insects. We have insects. So we have luminous, of course, non-luminous. So we talk about things that produce their own light and others that reflect off light from other sources. So we are really talking about the sun being arguably the greatest source of visible light. And of course, sometimes when there is rain, you see even the rainbow, the light is able to spread into the various colors. How do we detect ultraviolet? Number one is by the use of photographic film. All right. We also use photocells. We also use fluorescent materials and paper slightly smeared with Vaseline. Now, what is a photocell? A photocell, you've seen some special types of light system that actually switch on automatically in the event of darkness and switch off automatically in the event of light. So what those lights contain, they contain photocells which are able to detect that. So visible light and ultraviolet can be detected by this. Mostly ultraviolet will use photographic films, but even for photography in the past, for photos to be processed, there had to be a film that would capture the images, and then it had to be processed into a negative of the image, which then had to be processed into a hard copy photo. Nowadays, we are talking about digital cameras, which use technology we call CCD, charge coupled devices, and so on and so forth. So if you see, all these things that we apply in our daily lives have their basis in electromagnetic spectrum. Moving on to the next one, which is X-rays. Again, X-rays, we all know. So let me cap this. X-rays, we all know that in case you have a fractured bone or a dislocation, when you go to the hospital, they do an X-ray scan or an X-ray imaging. So, what produces X-rays? X-rays are produced in special tubes called X-ray tube by the action of a beam of fast-moving electrons hitting a metal target. Actually, our next topic we shall be now delving much deeper in is X-rays, and we shall see how in an X-ray tube, when you have or you manage to produce cathode rays, and then those cathode rays move, and then they strike this metal target at an angle at a very high speed, so X-rays are produced. So X-rays are produced by action of a beam of fast-moving electrons hitting a metal target in an X-ray tube. And how are these detected? Obviously, if you have had an X-ray scan, you saw the photographic plate or film as a detector, whereby the part with the scar or the part with the fracture, because of course it's an opening, X-rays will manage to penetrate through, and then the image formed, of course, will be devoid of that crack. So assuming that this initially was like that, and then X-ray beam struck. So we know that X-rays will be absorbed by the bones and of course penetrate the flesh. But then in case there was a fracture on the bone, they will still manage to penetrate. And that's how the image is generated on a photographic plate that the doc now examines and actually locates the position of the fracture. So X-rays can be detected using a fluorescent screen or a photographic plate. Now we're moving on to the last one. In this case, we are talking about gamma. Gamma, and this mostly gamma rays or gamma radiations. This gamma, there's another topic in Form 4 that shall be delving into much later called radioactivity. And we shall see that some of the atoms, they can become unstable, in which case they are able to split or to disintegrate in a process called radioactivity. And as they split or disintegrate, forming smaller nuclei, in the process they are able to produce particles called alpha, others called beta, and now radiation in form of gamma. So gamma radiation is a form of energy which is in very, very, very high quantities that come or is produced by radiation or radioactive particles at a very high frequency and possessing very high energy. And just to give you a very real example, if you are a student of history and government, you know what happened in Hiroshima and Nagasaki. So what happened, the US military deployed an atomic bomb that ended up releasing tremendous amounts of energy in form of gamma radiations, and that's what killed so many people in the two cities in the Japanese in the Japanese peninsula, and that's how the World War II came to an end, because these gamma rays, they possess colossal amounts of energy, because if the frequency of gamma rays can be anywhere from let's say 5.0 times 10 to the power 20, all the way to 5.0 times 10 to the power 24 times 10 to the power 24. So when we talk about this kind of frequency, and then you manage to multiply this now by the Planck's constant, you can see the energy, the humongous amounts of energy that gamma radiations are capable of producing. And that's now what, in the event of an atomic bomb, kills instantly, and much later the radiations as they enter the body, we shall see some of the dangers. So this is what we are talking about in terms now of applications. So they have, in terms of production and detection rather. Now, how about applications? So moving on to applications, we are moving on swiftly to applications. And if you are keen on the objectives, we said, number one, we should be able, by the end of this lesson, to describe electromagnetic waves. We should be able to state the properties. We should be able to, of course, state the uses or the applications, and much later maybe solve problems. For the problems you have already solved. Now, what are some of the applications? I will mention them very quickly, starting on with gamma. So where are gamma rays or radiations used? Despite the fact that we have said they can be dangerous, not all of them are dangerous. If you manage to produce low energy gamma rays, they can actually be used in medicine in a number of ways. Number one, in the treatment of cancerous tumors. So they're used to actually kill cancerous cells by exposing them to radiation. Actually, this is what is called radiotherapy. So if you've ever heard that terminology, this is actually the exposure of cancerous cells to radiation, and gradually these radiations are able to kill the cancerous cells. Number two, in medicine, they're used in the sterilization. In the sterilization of surgical equipment. So what happens, because these are high energy radiations, they are able to kill off any germ or pest on the surgical equipment. Let's say we're using the surgical blades or the pairs of scissors and so on and so forth. So they normally don't wash them when they are packaging them, maybe using soap and water or boiling, as traditionally some of us maybe have seen, but they are able to use more modern methods of sterilizing by exposing them to radiation. How about X-rays? X-rays, on the other hand, they are of lower energy as compared to gamma, but they share some of the properties. So X-rays, we know obviously they are used in the detection of fractures. Again, in medicine or in hospitals, detection of bone fractures. How else? In industry, how are X-rays used? In industry, X-rays are used to do what we call detection of metal flow. What that means, in case a metal itself has got a fracture or a crack, let's use the word crack. Assuming that a metal has a crack, and we know that some of the metals used, especially in aviation, they need to be very sturdy in case of anything. Sometimes you hear even planes coming down because of what we call metal fatigue. So to detect some of these things like metal fatigue, they use X-rays. In case of a fracture, the X-rays will be able to detect it. So detection of metal flows. I've already talked about that, detection of that. Crystallography is another area. Study of crystal patterns. If you, again, you want to study the crystal, let's say diamond, there's a way it should reflect light to know whether it's indeed genuine or not. There's a way you can expose it to X-rays and it will give a given pattern. We also have other examples of applications, including detection of forgeries, etc. UV radiations, they're used in medicine. Again, UV, they're used in medicine. as they supply vitamin D. We all know of vitamin D. Very early in the morning, everybody wants to bask in the sun as they enjoy the morning sun as it rises. That sun is full of vitamins. So some, as we shall be looking at much later, UV is of various types. Again, you have UVA, UVB, UVC. Not all UV is bad. So some of them will supply the much needed energy in form of vitamin D. They can also be used in the treatment of skin cancer. So skin cancer can be treated using UV, and we can also talk about analysis of minerals and also detection of forgeries. In case you've ever gone to the bank and you have, let's say, 1,000 shillings note, you find them illuminating some light on the note to detect whether it's genuine or not. In case it's not genuine, sometimes with the things, some things are added on documents. Let's say you are having a title deed or your KCSE slip or anything. There's something called watermark. So they put watermarks in between the layers, and that watermark can only be detected if that document is passed under UV. So it's sort of bluish. You're able to see that. For example, 100 shillings note, you'll see some marking there of 100, and so on and so forth. So nowadays, you don't look at banknotes against the sun. That's rather traditional. Looking for a lion. I've seen people trying to look for a lion inside a banknote. Indeed, those people who fake, they have managed to put the lion in the fake note. So we have advanced again ahead of the competition. So visible light is used in seeing, of course. Visible light. So without light, we cannot see. Without light, there can never be photography. So photography is one of the beneficiaries of light. Fiber optic, again, telecommunications, we talk about laser as well. So like for example, now we talk about fiber internet. So this is basically converting the signal into light, and then you pass it under a fiber optic cable. And since we saw that light travels very fast, that's why you see that fiber internet is very fast. So because we are using light. And then we also talk about lasers. Laser, just like I was talking about MESA, again, is more of a light amplification, and then that light is capable of moving in a very thin or narrow profile, and they are used by gunmen, especially snipers. They are used in construction, leveling, and so on and so forth. All these applications come in handy. So infrared, of course, we know it can be used in cooking, and so on and so forth. So how about radio waves? Radio waves, where can they be applied? Radio waves. Obviously, from the word radio, they can be used in radio communication. Radio communication, whereby a radio station or a television station is broadcasting over the airwaves using what we are calling radio waves. So widely used in radio communication. And we've seen that radio waves have the longest wavelength, the shortest, the smallest frequency, and they can easily be diffracted. On the flip side, we are talking about gamma radiations having very high frequency, but of course the wavelength is much shorter in what we call nanometers. Nano meaning times 10 to power minus 9. That range is something that cannot be seen using the naked eye. It's actually smaller than microscopy. It's actually subatomic. However, for radio waves, it's something that you can see. Actually, some of the wavelengths of radio waves can be as big, as tall as a building. So you can actually compare and contrast. So we are talking about one wavelength being as tall as a skyscraper and another one being smaller than an atom. So you can now see why they have the various applications in our daily life. So there's something else about waves, in this case radio waves. Sometimes you wonder why, despite somebody maybe living on the other side of a mountain, they will still be able to receive a radio signal or a TV signal, and yet there is a barricade, yet there is a barrier. Because these radio waves, they undergo very high diffraction. Diffraction is whereby a wave, when it encounters a barrier, let's assume this is a mountain, and somebody is living on this other side, and then on this other side now we're having a transmitter Remember, I talked about a transmitter being tall, and then it is broadcasting. It's sending all these waves. Now, as these waves reach this point, they are going to spread. They are going to spread, and this spreading is what we're actually calling diffraction. So if this guy here is having a radio antenna or a TV antenna, they will still be able to receive the signal coming from the other side, because these waves undergo what we call diffraction. They're spreading as the waves encounter an obstacle. Now, we have various types terminologies when talking about radio waves. I want to dwell a bit on this. We talk about FM. We have AM. You sometimes hear about SW. So for those of you who are in Form 4 right now, you obviously probably have not encountered these terminologies, AM and SW. We used to have radio stations transmitting using shortwave, whereby you'd even be able to access or to tune into radio stations broadcasting from abroad. If you tune into the shortwave, amplitude modulation, you find that some of the waves are actually, the modulation is actually on the amplitude, and some of the waves, the modulation is actually on the frequency. So the difference between FM and AM is that for FM, what changes is the frequency. What changes is the frequency, and for AM, what actually changes is the amplitude. And we've seen what amplitude is in terms of these waves. You say these waves travel like this. So this is the amplitude, and from here to here, that is now one cycle. So FM refers to frequency modulation, where now you're able to send signals at different frequencies, because imagine every television and radio station were transmitting at the same frequency, there will be something called interference. So to prevent that, these signals are sent or are transmitted at different frequencies modulation. That's why, for example, in Kenya, you would find a radio station transmitting, let's say one is transmitting at 106 megahertz, another one is transmitting at 99.2 megahertz, and it can go as low as 87 megahertz. So for radio, they can go as low as 87 and as high as 108. They cannot go beyond that. But then we know that as frequency goes up, you can also have other applications, including military. So there are some frequencies which you cannot access, but somebody, let's say a policeman holding his walkie-talkie, is capable of detecting. That's how you see some of them even communicating wirelessly using their walkie-talkie in traffic, and they are able to communicate without spending a coin. Sometimes you wonder how the policemen are able to communicate the whole day, and they do that for free. Actually, that's for free. They don't have to recharge their walkie-talkies with credit, because they are using a different frequency from the one that we use on our radios, and so on and so forth. So basically, that would be it. But then there's one more thing that we need to learn about this whole topic as we slowly bring into conclusion. We want to discuss something very important, and it's called the greenhouse effect. Greenhouse effect. Greenhouse effect. Greenhouse effect. You've probably heard somebody talk about global warming, and you've never known what that means. Now, radiations coming from the sun, remember the sun is our main source of energy on Earth. So the sun is a primary source of energy on Earth. So when the radiations and the rays coming from the Earth hit the Earth's surface, so this is the Earth, and remember again, the Earth has got its atmosphere. And in the atmosphere, you expect things like clouds, things like moisture and so forth, and so on and so forth. So what happens? These radiations from the sun manage to go all the way up to the Earth's surface. Some of them are reflected off, but most of them end up here. And in case there are many gases in the atmosphere, and one of the primary causes of this gas is CO2. We've all heard about carbon dioxide. You find that now, as the heat from now reflecting from the Earth's surface is now escaping, it's unable to escape this sort of blanket that is created by these gases, which we are, some of them CO2, others we have the CFCs, the chlorofluorocarbons and so on and so forth, the nitrogen oxides and so on and so forth, and the water vapors and the clouds. So this heat is coming one way, but then it is trapped. It's coming one way, but then it is trapped. You find yourself in a scenario where the earth is encapsulated in a blanket of cloud and gases that prevent the heat from escaping. So what is the danger of this? The danger of this is that if we have too much heat being retained on the surface of the earth, you expect those guys living by the sides of the oceans and those guys living by the sides of the mountains. Number one, for the mountains, because the temperatures will have increased, the ice on the caps of mountains will melt, and then it will flow in form of water through rivers and then end up raising the level of oceans. So what happens, you find that people living near the oceans, they are displaced by this water because now the oceans is slightly higher than it used to be. So this is one of the major concerns about global warming, and it's as a result of the trapping of heat. So when you hear somebody say global warming, it's also known as the greenhouse effect, because we simulate this in our farms by doing a greenhouse and put a green cover on top and side, such that the radiations from the sun manage to enter, but then the heat cannot escape. So in the greenhouse, then farmers are able to grow their crops all year round. Finally, what are some of the hazards? UV rays, gamma rays, I've said they carry very high amounts of energy, which of course, if you're exposed to, can easily end up damaging cells, burning your skin, and of course, in the worst case scenario, you know what would happen in the event of exposure to gamma radiations. So this can lead to things like cancers. We talk about leukemia and hereditary defects in children. So we find that some of the effects of the Hiroshima and Nagasaki bombing in Japan are still felt even up to date because of the hereditary issues. They affect the genome, or what you call the DNA. So the radiations enter the body, they affect the DNA, in which case now the kids who will be born after, they are born with a defect. You've heard about defects like hydrocephaly. You find some kids being born with maybe tiny eyes, big heads, and so on and so forth. They can be as a result of this. Leukemias, these are cancers that we can talk about. Cancer of the blood. So we find that some people can develop leukemia and other things like skin burns. Sometimes you see maybe when you move to the coastal region, you find some of the tourists applying some sun creams, some sun creams. So because if somebody is very, very light-skinned, it's not the same as somebody who is dark skin, because what will happen is that the dark skin is able to absorb and radiate. For the lighter skin people, they most likely will encounter skin burns and so on and so forth. So you need to be, as you are getting exposed to radiations, you need to be wary of some of the dangers. And how can you minimize some of the dangers? Number one, reducing exposure, because if you are overexposed to radiation, there's what we call dosage. That's why a doctor cannot recommend that you go and have a scan, let's say an X-ray scan every day. They are not going to allow something like that to happen, because they know, despite the fact that X-ray is helping detect fractures, on the flip side, those X-rays, because they possess high energy, they can end up damaging internal organs. So you reduce dosage by minimizing exposure time. And then we advise individuals to keep a safe distance from the radiations. So keeping a safe distance, if you have a radiation source, or if you have, let's say, X-ray machine operating somewhere, actually, if you go to hospitals, you see they actually write on the door there, danger. They write danger and no unauthorized access. Why they do that is because they would not like people to come too close to these radiations. And much later in a topic called X-ray, you shall see how the X-ray machine is designed to keep even the operator safe because the operator, remember, they use that machine daily. And number 3, you can minimize exposure by using shielding materials such as lead jackets. So shielding materials. So you find that those individuals who go, let's say they are running a nuclear power plant, they are wearing lead jackets. These lead jackets, because as we shall see later, some of the radiations can penetrate, let's say, one leaf of paper. Some of the particles will be stopped by an aluminum plate. Others will still manage to pass, but then will be stopped by lead. So we have lead, we have steel, and we have paper. So some will just be stopped by that, like the alpha, the beta will be stopped by that. But then gamma will go all the way to lead. So if you're wearing a lead jacket, you will not get overexposed to this. Now, I think I gave you 2 questions. By now, you should have found the answer. Green light has a wavelength of 5 times 10 to the power minus 3. Calculate the energy it emits. A certain radio station broadcasts on 100.3 megahertz. Calculate the wavelength of the broadcast signal. And probably you can try this question at home as we bring this to a halt. Calculate the frequency of a radio signal generator. Calculate the frequency of a radio signal generator producing waves with crests 1.5 meters apart. Take C equals 3.0 times 10 to the power 8 meters per second. Calculate the frequency of a radio signal generator producing waves with crests 1.5 meters apart, and you're supposed to take C, in this case the speed of light, as 3.0 times 10 to the power 8 meters every second. Now that, my viewer, marks the end of today's lesson. I hope you have really enjoyed, and these are some of the topics that really spruce you up to want to take up some of the courses at the university level, including engineering. We talk about electrical and electronic engineering. Some of the courses are very, very tantalizing. They'll make you even want to do some of these things more, and we welcome you to follow this program as we meet again next time. Bye-bye for now.